On scales far beyond human perception, there are strange beasts, exquisite palaces, wondrous landscapes. Some just a few thousandths of a millimeter long. Others dominate the vast expanses of the cosmos. Thanks to groundbreaking new technologies, I'm setting out to explore these hidden worlds.
Mind-blowing to look at that.
Each one of these dots is a galaxy. It's sending you a daily email from space.
At the tiniest and the largest scales, I'll see how the laws of physics have bizarre consequences, overturning everything we thought we knew.
My journey will take me to the frontiers of modern science, revealing our latest discoveries and our biggest unanswered questions.
This is the story of how the universe works at scales we can't normally see, from nanoparticles to galactic superclusters. When we move to scales beyond our imagination, the universe behaves in extraordinary ways. But about 3 centuries ago, when objects like this were first created, we had no real understanding at all of the true size of our universe.
You might recognize this. It's called an orrery. And it's a beautiful little mechanical model of the solar system. Now, it's not really a toy. It's been used for centuries to demonstrate the relative orbits of the planets around the Sun. But you shouldn't take this model literally, because it's not to scale, both in terms of the relative sizes of the planets and their distances from the Sun. Imagine the Earth were about the size of a football. Now, in reality, our planet is 12,700 kilometers in diameter. So this has been shrunk down roughly 60 million times. So what if we were to shrink the Sun down by 60 million times so it's the correct size relative to this Earth? How big would it be? We can now see just how wrong the orrery is in terms of scale, because the Sun would in fact be this size.
The Sun is over 100 times the diameter of the Earth. You could fit 1 million Earth-sized planets inside it. The Sun's mass is the source of its immense gravitational power over the whole solar system.
The next question is, on this scale, how far apart should the Earth and Sun be? Again, this is very different from the orrery, because if the Earth is here next to me, the Sun would be 2.5 kilometers away. The distance between the Earth and the Sun is actually a very significant figure in astronomy. You see, in space, distances are so vast that using kilometers soon becomes very impractical. And so astronomers have come up with their own units of measurement. And as it happens, the distance between the Earth and the Sun is one of them.
The Sun is 150 million kilometers from the Earth, a distance known as 1 astronomical unit. So our neighboring planet Mars orbits the Sun at an average of 1.5 astronomical units. The asteroid belt, containing millions of floating rocks, orbits at between 2 and 3 AU. Jupiter orbits at an average of 5 AU. Saturn at 10 AU. And Uranus at 20 AU. And Neptune orbits at an average distance of 30 AU. Many of us think this is the end of the solar system. But if you travel beyond the planets to about 120 AU from the Sun, you'll encounter a giant, mysterious structure which helps protect us here on Earth. It's a bubble called the heliosphere. The heliosphere was only discovered in the middle of the 20th century, but astronomers of earlier times did glimpse hints of its existence. The clues were in the behavior of comets, icy bodies of rock and dust which orbit our sun at different distances.
Comets have two tails which develop as they approach the sun, and they point in slightly different directions. One of them is made of dust, and it often trails behind the comet in a kind of arc. But the other straight tail, called the ion tail, is made of gas, and that's the one we're interested in. Here's the puzzle that baffled the astronomers of the past. The ion tails of comets always point away from the sun. It's as though there's a wind being produced by the sun. But how can this be possible? I mean, space is empty, isn't it? How can there be a wind blowing through empty space?
A clue to this cosmic mystery can be seen when there's a total eclipse of the sun. The sun has its own fiery atmosphere which shoots away from its surface. It's called the corona. It consists of colossal ejections, loops and flares of a kind of superheated gas called plasma. But the plasma extends far beyond the corona, out among the planets.
So the sun does have a wind. It's called the solar wind, and that's what pushes the comet's tails away from them.
The force driving the solar wind comes from the sun's intensely powerful magnetic field.
And I guess a lot of people don't realize that the sun even has a magnetic field.
Yes, it does, that's right, just like the Earth. Now, the sun's is a bit more complicated and it varies, it's a bit more dynamic, but the basic principles are just the same.
At its most basic level, the sun's magnetic field is quite similar to that of this bar magnet.
And you can see quite clearly that there are regions near the equator where the magnetic field lines are basically closed, they're closed loops, whereas over the poles the magnetic field lines actually point out further into space.
At the sun's surface, the magnetic field lines twist and turn, raising the temperature to millions of degrees. This heat makes the charged particles move so fast that they break free of the sun's gravity. The particles then flow out along the magnetic field lines to become the solar wind.
Here they're trapped, here they can get away far from the sun, and that's what forms the solar wind.
Tim has another demonstration to show how the solar winds create the enigmatic heliosphere.
Water coming out of the hose pipe, that's like the solar wind going away from the sun in all directions, and then it forms a boundary all the way around.
The water flowing outwards from the hosepipe collides with the water already in the pan, creating a turbulent boundary.
That's exactly what happens in the solar wind, and that boundary forms actually beyond all of the planets, something like 100 times further away from the sun than the Earth.
The water's forming a barrier here because the water that's already in the pan is stopping it from spreading out any further, provides a natural barrier. What's the equivalent to that when it comes to the solar wind? What's stopping that from spreading out into space?
Right, the equivalent boundary there for the solar wind is actually the tiny amounts of material that live between all of the stars. So we think of space as totally empty, but actually it isn't. There are tiny amounts of dust, gas, and even plasma-charged particles, and collectively we call that the interstellar medium. And that's the material that the solar wind hits that causes this boundary.
The interstellar medium, the stuff which the solar wind is flowing into, is mostly composed of gases, especially hydrogen and helium. Gases can move and flow, so in that sense they act a bit like water.
If we do think of space as a fluid, then the heliosphere is a bit like a boat carrying us through the interstellar medium.
Like the hull of a boat, our heliosphere helps protect us against the interstellar elements and the storms of space.
Space doesn't just contain gas and dust. It's also contaminated with irradiation produced by cataclysmic events like supernovae. Fortunately for us, the magnetic bubble of the heliosphere also acts as a shield, scattering and deflecting much of this radiation and preventing it from reaching us. So, in a sense, our heliosphere is like a life raft, carrying us through the vast and dangerous waters of space.
As it pushes its way through the interstellar medium, the heliosphere even creates a bow wave, just like the bow wave at the front of a boat. It's thought that most, if not all, stars have heliospheres. Our telescopes have taken photographs of other stars whose heliospheres are clearly visible. Sometimes we can even make out the bow wave. In 2020, the European Space Agency launched a mission to the Sun, a probe called Solar Orbiter. And among the scientists who built it was a team from Imperial College London, headed by Tim Horbury.
7:30, and we're due to launch in about 3.5 hours' time. It's really exciting, the tension's really building.
It's looking really good. 1.5 hours to go Solar Orbiter. You see it launch, and then we get this feeling, it's like a vibration of the launch because it's such a powerful event. Just makes you tingle because you know that it's your baby almost, off it goes. I'd already been working on the project for 13 years at that point.
Wow.
And to have such a personal connection with what was going on was incredible.
For Solar Orbiter's instruments to work at all, the engineers have had to protect them from the extremes of temperature near the Sun.
The heat shield is always pointed at the Sun, so wherever we move around, we orientate the spacecraft so that that is what's pointing at the Sun.
The instrument that Tim and Helen built is a magnetometer. It's mounted on a boom at the back.
The heat shield can get to temperatures of up to 500 degrees when it goes in close, but the electronics, which lives in the main body of the spacecraft, we have to keep that below 50 degrees. So from that front to the back, which is about 0.5 meter, we have to lose all that heat. And it's much better for us actually to be out here, because although it's cold, it's a stable temperature, and that really helps us to keep the measurements stable.
The orbiter takes photographs of the Sun's surface, and the magnetometer measures its magnetic field. The results are then sent straight back to Earth, to the delight of Tim and the team.
Do you want to have a look?
Yes, please.
So this is the kind of data that we get, and every day we can see what the spacecraft is doing and what the instrument is doing.
I mean, it's quite remarkable, isn't it, that it's sending you a daily email from space every day, updating you about the spacecraft.
It really is.
The orbiter has just started taking photos like this, a gigantic eruption of plasma from the Sun's surface. And the magnetic readings will help us understand why all this activity is happening. The aim is for Solar Orbiter to help unlock the mysterious workings of the heliosphere, the bubble which helps protect us on Earth. Every object in the solar system is held in place by the Sun's enormous gravitational power. And as we move beyond the heliosphere to around 100,000 AU from the Sun, it's thought there's one more massive structure out there, a sphere of icy objects called the Oort cloud. At these scales, we start using a new unit of measurement, the distance light can travel in 1 year. So the Oort cloud is believed to extend up to 3 light years in diameter. Now, traveling outwards, I'm going to leave our solar system behind. We now know that the beautiful ribbon of stars we can sometimes see stretching across the night sky is our own Milky Way galaxy. But around 100 years ago, most cosmologists didn't even believe there were such things as galaxies, and the universe seemed a much, much smaller place.
In the first decades of the 20th century, one of the biggest debates in cosmology revolved around a fundamental question: just how big is the universe? Many astronomers believed that everything we could see in the skies, in fact, every object in the universe, was part of one continuous giant structure of stars, dust, and gas, all clumped together. So the argument went, what we refer to today as our Milky Way galaxy was in fact the entirety of the universe. But some astronomers thought differently. They argued that our universe is composed of an unknown number of galaxies, colossal, independent islands of stars located at vast distances from each other. So our Milky Way would just be one galaxy among many. Now, if that idea was right, then the universe would have to be far, far larger than had ever been suspected.
The debate revolved around some mysterious objects in the sky, fuzzy patches of light called nebulae. Although they were very faint, improving technology meant astronomers could start to get to grips with them.
Telescopes of the time were even able to make out structure in some of these cloudy objects, like this large nebula in the constellation of Andromeda, photographed around 1901, 1902. Some astronomers argued that nebulae like this were relatively close to us, large clouds of dust, perhaps, where new stars were being born. But others argued that nebulae were independent galaxies in their own right, made up of billions of stars at mind-boggling distances away from us.
The debate was solved to a great extent thanks to the astronomer Henrietta Swan-Leavitt. For many years, her work was largely ignored, but it's finally being acknowledged by a new generation.
Henrietta Swan-Leavitt worked at Harvard Observatory about 125 years ago as a research assistant. We actually refer to them as human computers. But back then, computers were people, mostly women, who crunch the data and do things like measure the positions of stars, their brightnesses, make all these catalogues. She was absolutely dedicated to her work. She catalogued so many stars, looked at so many photographic plates over and over.
So here are some of Leavitt's photographic plates. Tell me what we're seeing here.
Yes, these are photographs of the night sky. They're negative images.
Leavitt dedicated herself to studying a very weird type of star, known as a Cepheid variable. These grow and shrink at regular intervals. So they pulse in brightness at predictable periods, which vary from days to months. Leavitt concentrated on looking for variable stars in 2 mysterious nebulae, the Small and Large Magellanic Clouds.
I find it hard to believe, looking at a picture like this, she managed to discover and catalogue 1,777 variable stars. Mind-blowing to look at that and think about how kind of painstaking that work must have been. And looking at these stars, she noticed something that I think really just changed our understanding of the universe forever.
Leavitt realized that there was a strict relationship between how intrinsically bright these stars are and how quickly they pulse.
So if we look at these 4 pairs of lights, the pair at this end are clearly the dimmest, but they also flash the quickest.
Exactly, yeah.
The brightness increases, but the flashing slows down, And at this end, these are the brightest pair, but they're also flashing the slowest.
And that's exactly what Leavitt noticed, that the brighter stars flash more slowly and the dimmer stars flash more quickly. And it's really what her main contribution to astronomy has been.
Here's the reason for its importance. If we see two Cepheid variable stars and they're pulsing at the same rate, then we know they must also have the same brightness. So if one seems dimmer to us, then we know that it must be further away. Leavitt had found a way we can measure huge distances in space. In 1923, Edwin Hubble pointed a telescope at the mysterious Andromeda Nebula, and he found that it contained a Cepheid variable. He measured its pulse rate to be very slow, 31 days. So, using Leavitt's discovery, he could calculate that it must be very, very bright. But because it looks so faint when seen from Earth, it must be very, very far away. In fact, the Andromeda Galaxy is 2.5 million light-years away. So the mystery of these faint, wispy nebulae was solved. As suspected, some of them are indeed collections of gas and dust relatively close to Earth. But others, like Andromeda, are their own independent galaxies, floating at unimaginable distances from us. So now that we can identify which celestial objects are part of the Milky Way, we can create a map of it, starting with our solar system.
Michelle, I can see the Oort cloud and the sun in the middle.
Yeah, so the Oort cloud is sort of the edge of our solar system almost, and we don't know exactly how large it is, but it's roughly 2 to 3 light-years in diameter.
Okay, let's see what else is in our local neighborhood if we zoom out a bit more. So what is starting to come into shot now?
Yeah, so Alpha Centauri is our nearest neighbor star system, so it's actually 3 stars. 2 large stars and 1 smaller, fainter star as well. Well, we can also see Procyon there. That's about 11 light-years away from us. And then we also have 61 Cygni over here. Compared to our solar system, we're talking about quite large scales now. But to people like me who study, other galaxies and the wider cosmos, this is still a really tiny distance. Like, for me, it's not even a real unit of measure until we get to, 100,000 light-years or so.
So all these stars that we're looking at here, they're just sort of in the way. You want to be able to see way beyond them.
Exactly. Normally, I don't worry about anything that's less than a few 100,000 light-years across.
So let's zoom out much, much further from the stars of our local neighborhood to encounter an important structure in our Milky Way, which is over 10,000 light-years long.
So what we're seeing here now is the Orion Arm, which is our local or our home spiral arm where we live. And spiral arms are kind of the largest visible structures we can see in spiral galaxies. And that's because they're full of the youngest, brightest stars.
The Orion Arm is home to one of the most famous astronomical objects visible from Earth, the Orion Nebula, a dense molecular cloud lit up by the stars it contains. It's well over 1,000 light-years away from us. Moving outwards from the Orion Arm, we start to see the whole structure of our galaxy.
Okay, wow. So there it is, the Milky Way galaxy. Where are we now in the Milky Way?
So if we start with the center of the galaxy here, where we have this bright elliptical bulge, we're about 25,000 light-years away from that, so up here.
And so how far does the entire galaxy stretch?
So we don't know exactly, but we think roughly from end to end, it's about 100,000 light-years across.
It's the force of gravity which creates all this structure. Gravity also draws in hot, young, massive stars to create the bright central bulge. In some regions of our galaxy, the interstellar medium is drawn together into areas of high density, where turbulence sculpts the gas and dust into astonishing shapes. These are stellar nurseries, where pressure from the force of gravity heats up the hydrogen, making it hot enough to ignite fusion. These are the places where new stars are born. But by studying the operation of gravity at a galactic scale, we've encountered a mystery. As our galaxy revolves around the center, what keeps it all together is the mass of all those stars and gas and dust acting as a kind of gravitational glue. During the second half of the 20th century, astronomer Vera Rubin pioneered the study of galactic rotation. She worked with instruments that could measure it with ever greater accuracy. As she did the maths, she realized something extraordinary. Okay, so we've shrunk the Milky Way galaxy down to manageable proportions, and we're looking at how it's rotating. Now, Vera Rubin was one of the leading figures who realized there was a problem with the way galaxies like this rotate.
Exactly, and so what we've got here is a simulation where we can set it up so we've mapped in all of the visible matter we can see, so the stars, the dust, the gas, and the galaxy. And now if we just set it rotating at the speed we know it's rotating at, we can see what happens.
As the galaxy revolves, it drifts apart in all directions, losing its shape.
Okay, so it's not holding together. There's clearly a problem.
Precisely, and this is what Vera Rubin realized. And the problem is, if we just take all the mass that we have here and add it up, there's not enough, it can't provide enough gravity to stop the galaxy from flying apart when it's rotating.
Rubin came to an astonishing conclusion. Either our theories of gravity don't apply universally at large scales, or there's a huge amount of matter there which we can't see. It's now thought that perhaps around 85% of all the matter in the universe is composed of what's known as dark matter. We can't detect it directly, but it must be there to hold our galaxy together. Most cosmologists now think our galaxy is surrounded by a halo of dark matter, a kind of scaffolding which keeps it from flying apart. Some estimates say it could be up to 2 million light-years across. The light we can see with our own eyes reveals just a small fraction of what's really out there. That's because many astronomical objects give off radiation right across what we call the electromagnetic spectrum.
This is the electromagnetic spectrum. On this end, you have gamma rays, which have the shortest wavelength and the highest energy, then X-rays, and then ultraviolet. On this side, you have infrared radiation, and then microwaves, and finally radio waves, which have the longest wavelength and the lowest energy. And this slice in the middle, this is visible light. It's what our eyes have evolved to see. The rest of the spectrum is, to our eyes at least, invisible.
In the past few decades, we've launched telescopes into space that can photograph the universe across the spectrum. And as we look beyond visible light, it's like pulling back a veil, giving us astonishing new insights into the very largest structures, things we never suspected were there. Astronomers take photographs of the same object with instruments sensitive to different wavelengths. They then combine these to produce images that our eyes alone would never see. These incredibly sophisticated imaging techniques have given us privileged glimpses of astonishing events, frozen moments from the birth, life, and death of stars and galaxies. our ability to penetrate the mysteries of the cosmos has also led to some bizarre surprises. Astronomers have found massive objects in space that effectively give off musical notes.
The obvious question that people would ask is, how can you hear sound in empty space? In space, no one can hear you scream.
Absolutely, but there are still particles in space, very diffuse gas throughout all of space, and it's possible for sound to propagate in that as ripples through the gas.
Using an X-ray telescope called Chandra, Andrew and his team took these photos of a region of space 250 million light-years away. They show massive energy bursts, shock waves rippling out through the interstellar medium. Each ripple is effectively part of a sound with a wavelength of cosmic proportions. Andrew has calculated that these sound waves make one of the lowest notes ever detected in the universe.
You've calculated that the sound is a B flat.
Indeed.
Which is why we're here, because George, who's the senior organ scholar here at St John's Chapel, is going to play us some notes.
First of all, George plays us a B flat in the mid-range of the organ. Every time George goes an octave lower, he has to double the size of the organ pipe he's using. 3 octaves down, and he's using the longest pipe at his disposal, and the note is getting to be as low as we humans can hear.
You can almost hear the individual oscillations.
Yes.
It's like a pneumatic drill. So we've gone down 3 octaves.
Yes, yes.
But to get to the sound,
We have to go down another 54 octaves. So we're going to have to keep doubling the size 54 times, and it would then be galaxy-sized.
the organ would have to be the size of a galaxy.
Yes.
The note is so low because the object only gives off one sound wave every 10 million years. The same kind of massive ejections have been detected again and again, all coming from the center of galaxies. This extraordinary image shows that millions of years ago, the center of our own galaxy gave off gigantic bubbles of energy, spanning about 50,000 light years. So what can possibly lie at the center of galaxies which give off these colossal outbursts? This is a panorama photo of our own Milky Way, but seeing what lies at the center is a scientific challenge.
In order to see what's at the center, why isn't it simply a case of pointing our telescopes at the core of the galaxy and just looking?
It's because of this black stuff. It's dust particles that lie between the stars. They're produced by the stars, but they're all over this interstellar space. Wherever you look, there is going to be dust. It's material that's not dissimilar from smoke, and you know how smoke blocks light. Essentially, it becomes impenetrable when you're looking along the plane of the galaxy.
Fortunately, dust is only a problem in the visible part of the electromagnetic spectrum. Andrew shows me the same view of our galaxy using a telescope that detects infrared radiation, not visible light.
And in the infrared, we can see through the dust. Looking through, we can see many more stars. There's 100 billion stars in the galaxy.
Most of the stars in our galaxy rotate around the center at roughly the same speed, about 220 kilometers a second. But that's not true for the innermost stars.
All of these stars will still be going round at 220 kilometers per second. But then as we get right towards the center, we find there's a group of stars which are actually moving in a strange way. They're moving much faster, and you can see that this one is swinging round in an orbit around something around there. It goes up to 5,000 kilometers per second, much faster, and something must be doing that.
It's by studying strange mysteries like the orbits of these stars that astronomers have come to an extraordinary conclusion.
The only possible solution for this, the only thing known to physics that we can fit inside that orbit and have that gravitational pull, is a black hole. A black hole with a mass of 4 million suns, and therefore there's a supermassive black hole at the center of our galaxy.
A black hole is formed when matter, such as a massive star, implodes, becoming so dense that not even light can escape its gravitational pull. It's now thought that there may be a supermassive black hole at the center of every large galaxy in the universe. In 2019, a team of astronomers managed to take the first ever photograph of a black hole in a galaxy called M87.
A key issue here is that the black hole itself cannot emit anything. Light only falls into it, it doesn't come out of the black hole. And what we can see is emission from material swirling round the black hole. And it's in what we call an accretion disk.
An analogy for the accretion disk of a black hole can be found in a kitchen sink. As water goes down the plug hole, much of it swirls around the rim. In supermassive black holes, some matter is swallowed, some swirls around, forming the accretion disk. The result is an astonishing buildup of heat caused by friction.
It gets to hundreds of thousands of degrees. All of the emissions from the accretion disk, which include jets, it releases an enormous amount of energy.
We're now pretty sure this is the answer to the puzzle of the giant outbursts. They're coming from the supermassive black holes at the centers of galaxies. Andrew believes these black holes have had a fundamental role in shaping the galaxies around them. The jets of high-energy particles and radiation are believed to have triggered the formation of generations of stars. Andrew has also found that these explosions of energy can blow the interstellar medium out of a galaxy, halting star formation. Galaxies come in all shapes and sizes. They range from dwarf galaxies, perhaps just a tenth the size of the Milky Way, to giant ones, many times its size.
It's now thought that there may be up to 2 trillion galaxies in the observable universe. But here's the question. Do all these galaxies just float around by themselves, moving through space serenely as independent objects, as lone travelers? Or do they come together as part of even larger structures? And how can we even answer that question?
Fortunately, to help tackle this puzzle, cosmologists can take advantage of a very peculiar phenomenon we're all familiar with here on Earth.
What you heard there was the famous Doppler effect. As the car approaches, the pitch of the trumpet is high, but as it passes me, that pitch drops.
The effect happens because as the car approaches me, the sound waves bunch together, shortening the wavelength and raising the pitch. As the car drives away from me, the waves are spaced out, lowering the pitch. Light waves do the same thing. When a source of light is moving towards us, its waves shorten, which moves them towards the blue end of the spectrum. When it's moving away, the waves are shifted towards the red. So by measuring the spectrum of light given off by a cosmic object, astronomers can tell if it's moving towards us or away from us. It's one of the uses of a technique called spectroscopy.
I'd like to give you an example of how spectroscopy works in practice. A few days ago, I asked my local astronomy club, the Hampshire Astronomical Group, to point one of their telescopes at the Andromeda Galaxy. Now, this is the nearest large galaxy to us and the one that Hubble used to make his big discovery. Using an instrument called a spectroscope, they were able to record its spectrum. And here it is. Now, there's a lot of science here, so I'll take you through gently. Here's the spectrum, this black and white image that was actually taken, and here it is again in all the colors of the spectrum. Now, this wiggly line here is the intensity of the light at different wavelengths, different colors that's coming from Andromeda. These dips here are signatures of particular elements in Andromeda, and this big one here is the important one. This is the signature of sodium. So you see this dark line here, that corresponds to the wavelength of sodium. Now, if Andromeda wasn't moving towards us or away from us, there'd be no Doppler shift, and we would expect to see this dip at a particular wavelength. We should see that dip between these two vertical lines. But in fact, you can see it shifted slightly to the left to shorter wavelengths or slightly towards the blue end. That means Andromeda's light is blue shifted, which means it's moving towards us. And from the amount of shift, we can work out how fast it's approaching us. You might well ask, so what? Who cares? But the remarkable thing is that by measuring a tiny shift in a wiggly line, we're able to calculate that the Andromeda Galaxy is heading straight towards us at 300 kilometers per second.
So, through spectroscopy, we've discovered our galactic destiny. It will take about 4 billion years, but Andromeda is predicted to hit our galaxy in a cataclysmic merging, which may even eject the solar system from the Milky Way entirely. Using spectroscopy and other observations, we now know that galaxies move through space in complex ways. Under the influence of the vast power of gravity, many of them are drawn together into what are known as galactic groups of up to about 50 galaxies. These groups can be drawn into larger structures called galaxy clusters of perhaps 1,000 or more galaxies. And these clusters can group together, forming the largest known structures in the universe, galactic superclusters. These consist of millions of galaxies and can stretch across distances greater than 100 million light years. In recent years, cosmologists have discovered the galactic supercluster which we are part of. Over the past decade, Professor Hélène Courtois of the University of Lyon has been working with an international team of astronomers on the epic task of mapping it.
Hello, Hélène.
Hi, Jim. It's nice to see you.
Hélène worked day and night using video conference calls to colleagues at radio telescopes across the globe.
These telescopes are in different time zones, so when do you sleep?
Yes, we sleep when we can. But I love observing, so I always try to be on all the shifts.
I've seen you describe yourself as a cosmographer.
Yes.
What does that mean?
So it's someone who is making maps. I try to find out where are the other galaxies compared to our galaxy, and then I measure distances and coordinates on the sky of those galaxies. And my specialty is not only to make maps, but to map the motions of the galaxies in the universe. So I am a dynamic cosmographer. I'm going to do galaxies all my life because what I want to see when I open my computer, I want to see beauty. So every morning I look at what the telescope have been running in the night and I see galaxies all the time. I don't want to do any other job.
First, Helene and colleagues plotted the positions of many thousands of galaxies, creating intricate 3D maps like this. Each galaxy is just a little dot. Then they measured the spectrum of every single galaxy to see if it's blue shifted or red shifted. And that meant they could work out the direction in which each galaxy is moving and at what speed. They found tens of thousands of galaxies all flowing in the same direction, forming a giant supercluster.
And they fly like this, like a dance. So the motions of galaxies are correlated. They travel together. They are not like with random motions. In some part of space, they travel together, and this is how we make this discovery.
In 2014, they made an astonishing announcement. They'd mapped the giant supercluster in which our own galaxy resides. They gave it a Hawaiian name, Laniakea. Its true size is incomprehensible to our minds, confined as we are to our earthbound scales, shapes, and sizes. But there are landscapes here on our planet which can give us an inkling of what Laniakea must be like.
To help us understand what these galactic superclusters look like, cosmographers like Helene often use the analogy of a river system, with smaller streams flowing into larger streams, which then flow into rivers, all heading towards the sea.
At the largest scales of the universe, galaxies move together through space along pathways which resemble rivers. The power of gravity makes raindrops fall into streams and streams to flow downhill into rivers. In the same way, galaxies are pulled by the immense power of gravitational attraction, heading to an enormous concentration of mass. So let me give you a tour of Laniakea.
This is our home galaxy, the Milky Way. And we live within what's called the local group, which contains some of the galaxies we've met before. For example, here's the small and large Magellanic Clouds. These are dwarf galaxies that were studied by Henrietta Swan-Leavitt. They're about 200,000 light years away. Over here is the giant Andromeda galaxy, which of course is on a collision course with us. It's over 2 million light years away.
Our local group stretches up to 10 million light years across, but it only forms a small part of the structure which Helene and her colleagues have discovered.
So let's see what the whole of Laniakea looks like. Each one of these dots is a galaxy, and each one of these lines is a pathway that they follow. Our Milky Way and all the other galaxies in our local group sit in one of the streams over there.
All of the galaxies are being pulled by incredible gravitational forces along these pathways. They're all moving towards a central mass called the Great Attractor. The Great Attractor is still a mystery, but it's thought to have the mass of trillions of suns, attracting galaxies across hundreds of thousands of light years.
And there we have it, our home in the universe. Laniakea contains about 100,000 galaxies like ours and 100 trillion stars. It stretches across 500 million light years. Looking at all of this, you can see why they called it Laniakea. It's a Hawaiian term meaning immense heaven.
These giant superclusters are only just being discovered, so we're only now starting to get to grips with the way they work. From earthly scales to the rotation of galaxies, the force of gravity is well understood by physicists. But it doesn't necessarily mean we understand how gravity holds these giant superclusters together. So cosmologists like Hélène use superclusters to investigate the workings of gravity at the very largest scales.
Our question, our physics question, is gravitation. How does it work on large scale? Does it work just like on Earth? And was it always the same in time? So we use the universe as a lab with huge masses, the galaxies. From the infinite small to the infinite large, it's the main question of physics of the 21st century. We still miss the full understanding of it.
By studying superclusters, a few cosmologists are beginning to question some of our most cherished scientific principles. According to our current model of cosmology, the laws of physics suggest that structures much bigger than Laniakea cannot exist.
If I look at this sheet of sandpaper, at this scale, it looks completely uniform. There's no pattern to it. But if I zoom in using this portable microscope connected to my laptop, suddenly I see structure, mottled colors of black and brown and yellow, shades and speckles, which are completely invisible when I'm zooming out looking at the whole sheet.
According to our current theory, a similar principle applies to the universe. After the Big Bang, matter was scattered pretty evenly throughout the cosmos because the same forces acted equally on everything. The power of gravity brought together galaxies and then galactic clusters, but over a certain size, gravity is too weak to bring structures together. Like my sandpaper, the universe should appear featureless.
This is what's called the cosmological principle, and it's one of the foundational pillars of modern cosmology.
But recent findings have cast some doubt on this extremely important idea. Remarkably, one of those discoveries was made by a student. Alexia teaches violin to students to help fund her way through her PhD. And while doing her research, she came across something remarkable.
It was really exciting, but completely accidental. My supervisor had this idea of using this new technique to map what's out there in the universe. And I happened to stumble across this giant, great structure. It was completely serendipitous.
The ingenious method which Alexia used involved very distant objects called quasars. These are immensely bright centers of galaxies billions of light years away, thought to be powered by supermassive black holes. For Alexia, they were extremely useful because she could use them as if they were spotlights, shining a light on the dark corners of the universe.
We're going to use these two torches to represent quasars, these very distant, powerful sources of light. Now, you have a simple demo here, this plate of glass. Tell me what these blobs are.
These little blobs here are representing faint galaxy and galaxy clusters. Now, without the quasars, we wouldn't be able to see them. They're too faint and too distant. But with the quasars, they essentially act like a torchlight that illuminates this faint matter.
As the light passes through a galaxy, some of it is in effect blocked.
We can see that some of the light was absorbed, and therefore something must have absorbed that, and therefore there is matter lying there.
Using this method, Alexia has been able to create a 3D map of a huge chunk of the universe, and she seems to have found a pattern. These red blobs are all galaxies or galactic clusters, and together they appear to form a giant structure in the shape of an arc.
We've used 3 different statistical tests, and all 3 of the tests show that the giant arc is actually more than just a random fluke.
That it's really there. Why is it so unexpected and exciting?
So we have this thing in cosmology known as the cosmological principle, and it says to us that on the largest scales there should be no structure or pattern in the universe. The cosmological principle has a specific cutoff limit, and that's estimated to be about 1.2 billion light years. But the giant arc here is over 3 billion light years wide, so it begs the question how something like that can form in our current understanding of cosmology.
The giant arc is so big that if we could see it from Earth, it would look 35 times bigger than our moon, even though it's 9 billion light years away. The reason it's so mysterious is because it's too big to be held together by gravity. And it's not the only one. Even bigger superstructures have been found, such as the Hercules Corona Borealis Great Wall, thought to be 3 times bigger than the giant arc. It's early days in the story, but this debate could be a game changer, because all our theories of how the universe was formed after the Big Bang are based on the cosmological principle.
Time will tell, I guess. It's still too early to be sure.
It's still too early, but everything is built on top of this assumption of the cosmological principle. So it's kind of like taking the bottom piece of a Jenga puzzle out and the whole thing collapses.
Carrying out investigations at these mind-boggling scales continues to challenge our most cherished beliefs, transforming everything we thought we knew about how the universe behaves and how we came to be here. And I can't wait to see what we discover next.